Okay, seems to have started. So good morning or good afternoon, depending on where you've joined us from. We've got a healthy North American contingent today. So good morning to you all. Welcome to our 153rd, I think, Reading Online Sports Economics Roses Seminar. We are generously sponsored by the Sport Economics Review, which is a new journal in the area of economics and sport. And as well as sponsoring this series, the Sports Economics Review is also sponsoring a conference we're going to have in Reading in May, which is a joint conference of the Reading Football Economics Conference and the Sports Economics Sports Management Conference. The one thing worth announcing at this point, which is quite exciting, is that the keynote speaker will be Colin Camera from Caltech. So we've got a very interesting and high-profile keynote speaker for the conference. I will post details about how you can get more information and even submit an abstract for that conference in the chat as we go along. And if you're interested in that and you can't access the chat, let me know and I can happily provide you with more information and direct you to the relevant websites. But I don't want to hold up Ray Fair any longer, our speaker for today. He is going to present on physical decline rates, men versus women. Ray, you've got pretty much as long as you like, so please do take away your presentation.
So thank you. Feel free to interrupt at any time. I prefer dialogue back and forth, so I encourage any questions or comments. So this work goes back to the early 90s, so it's about 35 years old now. And the model has not changed. The model I'm using is still the same one that I did in the early 90s. What's changed are the data. The data are now much better. And early on, the best I could do was using men's data. You know, the number of, in the 90s, so the number of like 80-year-old women running marathons was quite small. So I didn't have much data. So this latest paper, the data are now, I believe, good enough so I can compare men versus women. So this is basically an update of that. The problem with trying to estimate decline rates is the survival bias, that you can't just look at times in races by age and expect to get any kind of a decent decline rate estimate because of the survival bias, survivor bias, that good runners stay around and bad runners don't. I've refereed many papers in which they've done exactly that, where they just take the Chicago Marathon and look at the average time of those 50-year-olds, 45-year-olds, et cetera. And many of those results show, as you might expect, that things get better for a while. Right? You improve between age 40 and 55 because of the bad runners dropping out. So you can't do that. So what do you do? So what I've done is to look at world records by age. So I take the best time ever for a woman. So let's say I take the marathon, the best time ever run by a woman age 40, best time by a woman age 41, etc., and go out as far as I can. So there I'm getting what I hope to be some estimate of the biological limit, the biological frontier minimum time, in the sense that this is the best time ever run. So there's a large sample behind these world records, because many 40-year-old women have run the marathon, and I'm looking at the very best one. So in some sense, it's a large sample. On the other hand, the times are still many times I would say are still what I would call soft, and that's going to be a problem that's plagued me from the beginning. What I mean by that is that the time that, say, an 80-year-old woman has run, the best ever, the world record, it may not last very long, that as more elite women move in to the age 80, probably that world record is going to fall, right? And it will true for men as well, but in general, some of these times are probably soft in that sense. So what I do in the data, which I've done from the beginning, is to drop what I call dominated times. So if age 55 time is lower, better than an age 54 time, I drop the age 54 time. I just don't put it in the data set, thinking that the age 54 is soft, the idea that you don't improve with age at that age, so everything's getting worse. So if it's not getting worse, it must be that the time is, for age 54 in this case, would be soft, and I drop it. Okay, so that's the data. I think the next. Let me see if there's any. So I've done this. I can guess I can share a screen now. So you can. So these are the. Stop me, by the way, James, if something's not working. I'll just assume it's working unless you tell me. So these are the events that I'm looking at in this paper. I've added rowing. It turns out that rowing, these rowing machines have an amazing amount of data, and the data seem quite good, and for both old men and old women as well. So I've added rowing. Swimming has always been pretty good, and I've got running. So this is what I'm looking at in this paper. In the past, I've done other events. I've done track and field events, high jump, sprints, etc. Again, the data are in those papers not quite as good as these data. I've also done chess. Most of you will be like to know chess decline rates are much less than anything else. So if you are a person of the mind, this is encouraging for our business rather than physical business. So these are the events that I'm interested in. And so before I give the model, I thought I would just show you basically what I'm trying to do. So I'm going to go down to one of these figures. So let's take swimming 200 meters. The assumption that I'm making is that the decline rates are linear up to some point, and then after that become quadratic, okay? And these are in percent terms. It's important that they be in percent terms because a 3-hour marathon person, percent declines, et cetera, it's going to be different from a 2-hour and 10-minute marathon person. So I want to look at the assuming that the decline rates are in percentage terms. So these are percentage terms. I'll talk about in a minute. I do something different between 30 and 40. The decline rate, percent decline rate between 30 and 40 is probably something there, but it's not that much usually. So I don't want to assume that it's the same as after 40. So the assumption I'm making is that up 30 and 40 is 1% decline rate, linear, you'll see. And then it's linear between 40 and some what I call a transition age, at which it then becomes quadratic. And the advantage that I can do is I can actually estimate that transition age. You know, how far you go out before you start to slow down more than linear in percent terms. So I can estimate that transition age.
Great. Yeah. Can I interrupt you? Daniele has a question for you.
Yeah, it's just that we can't see the bottom of your slide. I don't know if that's deliberate or not.
I'm sorry, say the what?
The one below. The graph below we can't see.
We can't see the full slide. We only see the.
Can you see this one?
Yes.
Yeah, that's the only one that I need.
Okay, now. Sorry about that. Yeah.
Yeah. Yeah, I don't need the other one.
Okay.
So and then the one that becomes quadratic, I've restricted the quadratic at the transition age to touch the linear line and to have the same derivative, same slope at that line. So I've got two restrictions on in the estimation that you can kind of see in this. So the basic aim of this is to estimate this this line. And the data that I'm using, remember, I got data for age 40, 41, et cetera, but the data exclude any dominated times. So that's the restriction. So now let me go to the model and show you what I'm actually estimating. So the RK is the log of the record time. So this is the world record by age for some race, say the marathon, or K is the age. And that's assumed to be equal to the observation I have is equal to the biological minimum B sub K plus an error term. And that that's the model. Now, so I want to model, so how do I model the biological minimum? So this is what I just said, that up to some age K star, the decline rate is linear. Remember, B is in log, so it's all percent. So it's linear up to some age K star, which I estimate, and then it becomes quadratic. So really rather simple in that sense. And these two restrictions are what I said before. They have to touch at K star and have the same derivative of K star. So if you move out the math, that gives me this these two restrictions. And so that's it. If you then combine the model, you get the observed log of the world record time is a function of K, and then this dk is this 0 if it's linear, if K is less than K star, and 1 if it's greater. And then this is the quadratic term. So the estimate that I need, what I need to estimate then is beta, alpha, and delta, and K star. So I have four things to estimate subject to the restrictions. And you can, this is a nonlinear estimation problem, but it's easy to handle nonlinear estimates these days. So that's no issue. But the other, and so you can just do nonlinear least squares, which is what I'm mostly doing in this paper. But it is the case that you expect the error term always to be positive, right? It should always be the case that the record time is not less than, the observed time is not less than the biological minimum. So epsilon t, going back to the definition here, epsilon t should always be positive, right? That you can't do better than the biological minimum. So I can then, if I want to impose that restriction, it's a kind of a frontier, kind of interesting econometrics. There's a frontier, there's a nonlinear plus also a frontier estimation where you estimate under the restriction that all the errors are positive. And so I can do that. So I call that the frontier estimation method. And it's, again, numerically rather straightforward to do. It turns out it doesn't make much difference, I would say. So it's cute, but not absolutely necessary. But logically, you would want to do that because epsilon cannot be negative. So that's the that's the estimate. So it also may be that I can, again, stop me if there's any question on the model. So it also may be the case that I can pool and you'll see for the rowing events, it looks like I can pool. So what does that mean? So what I'm assuming is that for more than one race in rowing, more than one distance, maybe the alpha and the delta and the K star are the same. And the only difference is the intercept, the betas. Obviously, they differ because longer races take longer to row. So this is the model that I would use if I'm pooling. It basically, I'm still estimating for just alpha, delta, and K star, but also then estimating more than one beta, depending on how many races I have. So you'll see in one case, pooling looks like it works fairly well.
Ray?
Okay, so that's
Ray, I've
that's
got a
it.
question
Now
from Dennis.
that's yeah. Sorry,
Go ahead, Dennis.
go ahead.
Yeah, just a clarifying kind of a question. Do you have any controls for weather or course, anything like that? Because a world record set indoors versus outdoors at some level, or on a windy day, what are there any kind of controls for those things?
Well, all the events are either indoor or outdoor, so there's no mixing of that. But no, I don't do for the weather. This is just assuming that if it's that there's been enough people running the race so that the world record time would be probably at the optimal weather time as well, right? And so no, I'm just looking at the very best time ever. So that doesn't mean that a person can necessarily set the world record if the weather sucks, right, in that race. But I'm not really interested so much in that as just in seeing what is the best anybody could ever do under ideal conditions, right? Which is what these world records in principle are.
Okay, thank you.
Yeah. All right, so let me do 30 to 39. As I said, I used to just start at 40 and forget. I can just start at 40 and forget 30 to 40 and just not put in this model and don't take a stand on what happens below 40. But people were complaining that they're slowing down when they're 37, 38, and I'm not modeling that. So I decided I'd try doing that. So this is a way in which I try it. Say to age 30. There's a world record, let's say for the marathon, that may be set by someone who's age 27. But I'm just going to assume that the age 30 time, if it's not the world record, is soft. And so I'm going to use for age 30 time the world record, regardless of what age it was when somebody set that. Okay, so that's one point. And then I can back out from what I've just told you, the predicted time for age 40, which is this B hat 40. So it's the predicted time that for in this race for age 40. And then I just draw the straight line between the world record at age 30 and B hat 40, and assume that that's the slowdown rate between 30 and 40. And again, you'd expect that slope to be less than the alpha that I'm estimating starting at age 40, because most of the decline probably doesn't take place until 40. These are all linear quadratic. I mean, this is all percent linear things. So anyway, that's the way I handle 30, 40. The results are okay. You'll see they're not terrific, but I'll show you what I get when I do that. Okay, finally, before I go to the table of results, I compute these age factors, which I'm going to call RK. So this is in log, so I want to get the absolute. So e to the BK is the time at predicted time, the biological minimum time at age K, and I'm dividing that by the world record ever which is at age 30. And so that's how much you've declined between 30 and age K. All right, so that's it. This is just a number in the tables. Okay, so I'm ready now to go to the data. And this is a messy table. There's a lot in this table. So I'm going to try and stop me if this is completely unclear. I'm going to try to go through this piece by piece and tell you what the table is. Goes down to the end, but let me start with this. So I got the estimate. M is men, W is women. I've got the estimate of alpha. That's the slope coefficient between 40 and the transition age. This is the transition age. So one thing already you can see, the transition ages are kind of between about 60 and 75. This is the quadratic term. So this is once the quadratic hits, the delta hat is how big the quadratic decline is. And then this is the slope of the between 30 and 40 divided by the slope after 40, the alpha hat. So I'll come back to this number in a minute. Then these R's are the decline, how much you've declined from age 30, from the best, to age 70, age 80, and age 90. So this kind of gives some sense without staring at the delta hat coefficients of how much decline there's actually been. The number of observations is how I got per race. These are the number I'm actually using. So this does not include the dominated observations. Maximum age is what it says. It's the oldest age that I can get decent data for. Half is the kind of interesting thing. It's the age at which you decline by 50% from age 30. So like in this first thing, 75 means that at age 75, men have declined by 50% from their best from age 30. And then the standard error of K star, all these coefficients, of course, alpha hat and delta hat are highly significant. You know, there is slowdown. So it's not that interesting to test whether alpha hat is zero, say, because it's not. But what is kind of interesting in terms of getting the precision is how much confidence do I have in my estimates of the transition age, the K star, and that that's the standard error here. So like for men, for this first line, the estimate is 73.9 is when you start the quadratic, and the standard error is only 1. So basically, the precision of these ages is pretty good. Okay, so I'm going to now focus on, in terms of trying to go through this table, the first thing I'm going to do, well, actually, maybe before so I'm not going to spend much time on this. Is the nonlinear least squares estimates. The paper also has these frontier estimates. So this is the same thing, except I'm constraining all of the coefficients, all the errors to be positive. And so these are these numbers. I don't think there's questions I can take. I don't think I'll spend time on this. This is very close to the nonlinear estimate. So even though it's kind of cute to do, it doesn't make much difference. So I'm going back to table 2 nonlinear. So let me look at there's a couple of bad ones, and I thought maybe let me get the bad ones first, and then we can talk about the others. So there's two bad ones regarding women. One is the third one, the 10K for women. You can see that the transition age is quite high, as is the quadratic coefficient. These are correlated, these estimates are correlated because the bigger the transition age estimate, usually the larger the delta hat, because you've got a less of the quadratic to go and you're picking up really old people. So these tend to be positively correlated, but these are high, at least the 0.02 is high. And you can see that the R90 for women is 6.24. Again, stop me if this is not clear, 6.24. And for men is 2.83. So the difference between men and women is unrealistically large. So so that's not, so basically for this particular race, old women I'm not doing well on. Not too bad up to 80, but after that, basically after this 82.7, the predictions are way off. So that's something that you're just basically going to have to wait. I attribute this basically to soft times at the old ages for women, and I just need to wait for more world records before this becomes better. And there's a similar problem for the marathon, RUMAW down here. The transition age is not bad, but the coefficient of delta is fairly high at 0.002, and that leads the R90 to be 3.49 instead of 2.48. So it's too big, I think, basically. So this is another problem that will only get better with more world records. Unfortunately, it's the marathon that does this because that's one of the key races here, but it's probably not too bad for women, but up to 80, but I wouldn't trust it beyond that.
Wait, can I ask?
Okay, those are the two bad ones.
Wait, is the R is the units for the R is some kind of ratio, is it, or is it hours?
It's a ratio. It's a ratio, yeah.
Okay.
It's a ratio of the best time at age, the world record time at age, or time at age 30. These are all world records, and the predicted time at age 80.
Okay, great, thanks.
Okay, now let me do, this is not quite as important, but let me do the slope. So you expect the slope between 30 and 40 to be less. So you expect this ratio of the slope to alpha hat to be less than 1. And it is for the most part, but there's a few cases in which it's greater than 1. And if it's greater than 1, then it just means that the 30, the decline between 30 and 40 is larger than the decline linear thing than a decline after 40, which is probably not sensible. But so there's a couple of cases in which this is greater than 1, and that's again something you need to wait for more data. And then if it's less than 0, which is, I think in one case here, I've got the minus 0.07. So it's basically 0. But if it's less than 0, it means that the predicted time at age 40 is less than the world record. Right. And so, because remember, this is predicted time, age 40 from the line. So this is also not, but this is basically 0. So I have a couple that are, here's down here for, it's 1.08. So that basically just says that the time between 30 and 40, the decline is the same as after 40. Okay, so that's the bad stuff. Now let me get to the good stuff. So one thing that's remarkable is these are the rowing events. And if you look at the coefficients for men, they're really quite close across these races, 1,000 meters, 2,000 meters, et cetera, across these distances, these rowing machines. So it looks like I can just pool, because I basically assume that the alpha is the same for all of these events. and for men, and then all the events for women. So I do that. I estimate that pooled regression, and I get the last line here. So this seems I would put a lot of confidence on this because it's based on a lot of observations, pooled, and fairly precise estimates. So that's the pooling. So that's the good thing. The standard errors, another good thing. Standard errors, as I said, of K star are fairly low, except in a couple of cases. RO 100W, the standard of 13.9. But otherwise, the K star transition age is estimated reasonably precisely. Okay, so any question? Yeah, let's say a question on this table before I go to the next table.
Yeah, so if you could just show us how do those pooled ultimate results compare to the unpooled?
Yeah, that's down here. Here's the pooled results. Let's say for men, the coefficient on alpha is 0.0047. So that's the linear decline rate, percent linear decline rate up to age 64.6, right? So then you can look to see for the 1,000 meters, instead of being 0.0047, it's 5.2. For the 2,000 meters, it's 4.9, 5.1, 4.1 for 6,000, and 4.2 for 10,000. So the individual estimates are what I just said, and if you pool them all, you get 0.47. The transition age, if you go down by event for men, 63.7, 65.6, 65.4, etc., and the pool is 64.6. So they're all so close together that as I said, it seems possible to pool. Less so for less so for swimming, and certainly less so for running. I have in the past pooled some events, and I could possibly pool a couple of the running event, but I didn't for this. Okay, so we still don't know, and if you look at the half, these times are the age at which you lose half. They're usually in the 70s. In some cases, swimming is in the 80s. So it's, as I'll say later, and rowing is in the 80s. So you can go out even older than I am and still not have lost quite half, right? So, so now how do we look at these? Is there a more intuitive way to look at it? So this is a table that I think maybe gives you some sense of the data. So I'm looking now at R80, basically looking at R80. So it's the percent decline between 30, the world record, and the predicted world record at age 80, right? So it's that. So what is the percent decline? So let me do the pool first. So the rowing pool, which I have a fair amount of confidence in, the percent decline for men is 33%, and for women it's 42. So the difference, which is what I'm interested in this paper, is of 9 percentage points. For swimming, it's greater than it is for rowing, for both genders, but more or less the same for both men and women. So I think you would look at these results and say that probably within standard error or something, that men and women are about the same in terms of their decline rates. But for running, remember there's a couple of problematic ones. The women 10K, which is 75, and the women's marathon, which is 89. Both of those are a little flaky because I don't have good data, but this only goes up to 80, so it's not quite as bad as the table indicates, because that's more or less after age 80. But you can see there's two things that these times are the percent declines are much larger than for swimming and certainly larger than for rowing. And the differences between men and women are larger. 18 for the 5,000 meters, 11 for the 5K, et cetera. So this gives you some sense of what the results in table 2 are showing in terms of how fast you decline. And I mean, basically what this allows you to do is compare across events. I think you would conclude that rowing is the least decline, then swimming and running, and then comparing across genders, which is about the same for swimming, not quite as good for rowing, and not good, much larger for running. So for some reason, women don't, whatever running does, at least according to these data, decline faster. And then the other thing you can do is, this is just for age 80. So you can, but then if you can plot things to see, how they work. So I've taken 3 of these events. I've taken the half marathon for running. I didn't do the marathon because, as I said, the women numbers are somewhat problematic. So these are the 2 ages, the 2 equations that, for half marathon for men and women. You can see that the decline rate between 30 and 40 for women, you can see where it is less. It's gonna, from the plot, it's obvious it's less. For men, it's a little bit less, but it's not really noticeable in the graph. So and this is out age. So the distance between men and women is getting a little bigger. This is in percent terms as you go out in age. What I just looked in table 4 was at age 80. So basically, the age 80 is what table 4 shows, but this shows all the ages. So this is for the half marathon, and then the same event. This is the percent decline since 30. Again, I guess at 80 is what I'm doing. You can see it's getting a little bigger. I guess this is a better graph to look at. It's getting a little bigger as you get beyond 80. And then, so that's for the marathon. Then for swimming, where basically I said it looks like they're about the same in terms of decline rate. Obviously, the men are a little faster, or are on average faster than women for age, and at least in 200 meters. But the decline rates are very similar, right? So this is basically shows that for this particular event, men and women are about the same. You certainly wouldn't conclude anything otherwise. And for rowing, this is what it looks like for rowing, and this is the decline rate. Remember, 80 is what I'm using. So again, for rowing, it looks like that the gap between men and women, how much you lose as you age, is a little worse is getting worse for women relative to men. Now, could be, and I say this in the conclusion, but I was going to do it now. The question for something like this is that if it's the case, either this one or the this one for men, for the half marathon, if it's the case that there's more soft times for older women than there are for older men, so that if we wait, let's say, another decade and look at the world records that are set by 80 plus men and 80 plus women, if it's the case that more world records are set and larger distances, larger time changes for women than men, then these lines of women are going to move closer to men, right? though. So if basically if some of these, if the soft time problem is more for women than for men, which will be changed later as we get more and more old women running, elite old women running, then this distance will probably change. Now, will it, one interesting question, which I don't have an answer to here, will it be the case that, say, 30 years from now, when you got a lot of women, new women age records, will it be the case that these lines are now the same like they are for swimming, right? And also the same for rowing. So will this gap disappear? My sense is that at least for running, the differences are big enough that that it's unlikely. That it does seem to me that women do physiologically slow down a bit, and that will hold up. But that'll be tested over time as we get more world records. Okay, so I got three other things to do. Well, I got about 20 minutes before. Okay, well, then I take the whole 20. So I got three other things to talk about. One is the conclusion that what do you take away from this paper? And the first conclusion that I take away is that the decline rates, I think this is an optimistic paper. The decline rates are not bad. As you can see that how old you are when you lose half, etc. So you can stare at these numbers, but it looked to me like it's fairly positive for humans, that we're not that bad even at age 85. The second conclusion is that decline rates are larger for running than they are for swimming and rowing, and probably larger for swimming than for rowing. So there's some at least distant differences between the three events in terms of slowdown rates. Running is the worst. And then the question about men versus men, I've already done this third conclusion, that this suggests that for swimming is the same, rowing not quite, but not too bad, running much larger. And then the question is whether comparing men and women, will that hold up over time or not? So that's the main, the three main conclusions from this. So that's point one. Point two is I haven't mentioned, is this relevant for anybody other than elite runners? And people differ on this. I have friends who I've tracked over the years who are right on their line. Each person has a line because these are all in percent terms. Of course, the intercept is different because these are not elite runners, but conditional on your best time at age 30. Then you look at your percent declines. Are they the same as I've estimated the biological frontier to be? And for some people, yes. I've got a couple of really people quite close to the line. So the question I think what I need for people to stay on their line is that they stay in peak shape. They're not sick. Also, they're not injured, and they're in peak shape, and they're both mentally and physically, right? So you get these gung-ho athletes, gung-ho people that are doing that, and then I can look at their time as they age, and if they stay that way, they don't become couch potatoes or get injured or sick or something, then are they on the line? So if you assume that, and some people are, so this doesn't pertain just to elite athletes, because I'm looking at percent decline rates, not levels. So it may be that you decline in percent terms about the same as elite athletes, which is a much weaker assumption than you are going to be running a race that's the same time as an elite athlete at your age. So anyway, so that's, frankly, personally, I'm declining much faster than my line. So I'm afraid for my case, I'm not on the line, unlike some of my friends. So what can I say? All right, so that's point 2. Point 3 is I've looked at the marathon qualifying times for for these main marathon races, and so and it's kind of cute what I get. Let's take Boston Marathon qualifying times. So the qualifying times are listed in the first column. 3 hours. Let's do men. 3 hours for men. Then it's 35 to 39, 3:05, etc. All right. And then look at my times. I start out at 3 hours, and then I use my estimated decline rates to figure out what the qualifying time would be if you're following the biological frontier, starting out at 3 hours for age 30. And you can see the first 2% declines are 1.2 and 1.2 because that's the distance, but that's the line between 30 and 40. And then after that, basically between about 70 and 40, the decline is the same. It's all linear. Percent terms is 5.5. And then the quadratic begins to kick in, and it's 5.6 and 5.9, right? So using those decline rates from the estimates we've just looked at, I get these fair times, which is the time that would be. So they obviously differ somewhat from Boston, but actually, by the end, 435 versus 429 is not too bad. But my complaint about Boston is that these percents go up and down. The assumption of all this work is that nothing gets better with age after age, say 40 anyway. That you're not going to improve. That it's just a fact of life. And here, according to the BAA percents, you are improving. The decline rate between 45 and 49, or between in the 49-45 interval relative to previous interval is 5.3%, but then the next interval is down to 2.5. So it says that you're declining less as you get older. Then you go up again, up to 4.9 and 7. Then you go back down to 6.5 and 6.1. So these numbers should either be the same or they should be increasing, right? It should never be the case that you're going to get better with age. So they don't have the biology right, is my argument. And it would be only a small tweak for them to get the biology right. You just basically want their percents to be constant or increasing with age. And that's the same problem for women. They got, a 4.5 decline between 45 and 40 between this category and that. And then it's back down to 2.2 again, et cetera. So it's all over the map, 6.1 and then back down to 5.2. So again, they just don't have the biology right. The other thing that, for Boston at least, the world record for a marathon woman versus men is about 9.4% more, right? But the Boston does 3 hours for men and 3:30 for women, which is much bigger than 9.4%. If you did 9.4%, you get a time of 3:17. So if you start out at 3:17 using my decline rates, then the fair 2 time is what I've got in this last column. So that basically you're at the moment, this is a positive, it's biased in favor of women because they got such a much bigger starting point relative to world records. Okay, finally, London. You guys are in London. Some people are in London, right? So is London the same way? And it's to some extent even worse. You've got, but it goes out further. And remember, if you get much beyond 80, then things get a little bit dicier, especially for women. But you know, going up to 80 is probably not bad. You can see that the times for London, you know, goes up to 12.5% between 60 and 55, and then down to 6.7 and up to 25%. So this is completely wacko, right? No, this is completely contrary to the biology, the assumption that you never get better with age. And the same for women, even worse. So London is also not is inconsistent with biology. And then again, the qualifying time for women for London is 3:45, which is even worse than 3:30 for men. So if you do 3:17, you get quite different numbers. As I wouldn't trust for this much beyond 85 and beyond. Probably don't want to trust the numbers, but before that, it's probably not too bad. So Mike, I've tried to write these people and tell them that they don't have the biology right, but I'm not getting very far, I would say, so far. Boston, I did talk to somebody at Boston, but they either don't understand it or they're not interested. I can't quite figure it out. But anyway, that's the use of this work for practical qualifying times. Okay, so let me stop there and take questions. So I need to get back.
Yeah, I think if you unshare, but you might want to refer back to your numbers at some point. So maybe worth just leaving it there for now, Ray.
Okay, am I back now?
Yeah, you are. Yeah.
Okay, good. So I'm happy to take questions.
Great, super. Thanks so much, Ray. Really, really interesting stuff. I think Wayne looks like he's itching to ask a question, and Bernt's got his hand up. So we'll check with Wayne first, and then we'll go to Bernt.
Yeah, so two things. One, I'm wondering about doping, and I assume that, you know, whatever doping scandals there've been, that hasn't really changed the records very much. But so that's just kind of one question. I assume there aren't like outlier, you know, world records that have then been reversed with doping or something like that. That's one question. And then I'm really interested. So you got data sets of average runners and average rowers and all of that over time, correct?
I'm sorry, say it again.
Oh, I realize that the focus of this work is the decline from world records and how that declines over time. But does your data set also include runners over time and participants over time?
No.
Okay. Yeah,
no.
But so separately, you've got some of that stuff.
Yeah, right. These are just world records. So I'm taking it. So I argue that I have like thousands of observations at each age, right, and I'm taking the best one. Yeah.
Yeah. So for that separate work, I'm interested in, you know, for average participants over 30 years or so, kind of, you know, that's it. But this is entirely different than what you're doing here. But what about the doping? Is there any issues there with world records being rescinded?
You know, I don't have data on, I'm just taking down doping. I just have the world records that these official agencies do. So I assume that they try to monitor doping. I don't know for rowing, you know, it might be if you're rowing in your house and stuff, how they can quite monitor. So it could be that's a problem. Or also related, it could be, if you get some, let's say freak, I don't want to be pejorative, but some freak person that is just heads and shoulders above anybody else, right? And he or she runs amazing time. So that person's in my data set. And if it's an old person, it can affect the quadratic estimate quite a bit. And so it's not a person that's doped. It's just a person that for some reason has DNA that's different from almost anybody else. And I don't really want that person either, right? Because I want to try to get a reasonable biological frontier, but not necessarily these really extreme outliers. So that's another problem that I have, even if the times are correct. And doping would be similar. If somebody dopes is then better than the biological thing where you're not doping, and that would also skew the results that I've got. So yeah.
Right, so some strange outlier, artifact. Exactly, yeah.
Yeah, that's right.
Great, thanks, Wayne. We'll go to Bernd next.
Yeah, thanks a lot for this interesting presentation. I have one explanation for why the decline rates are much larger in running than in both swimming and rowing. Running is, contrary to the other two sports, dominated by elite athletes from East Africa. And these people have not yet reached the age of 60, 70, 80. So in 20 years from now, I'm pretty sure you will observe the same decline rates for runners than for swimmers and for rowers.
It could be, yeah. I don't have any way of testing that now, but yeah.
But I'm pretty sure that the world record holders in running who are 70, 80, 19 years old all come from either Europe or the US, and none of them comes from Africa.
Yeah, that's probably right. That's probably right. Comparing what that would do to my results, if you compare men versus women, neither gender is from Africa is in the data. So if both of them enter, could be I still keep the gap between women and men, right?
Yeah, but female elite runners arrived about 10 years later in the big city marathons than elite men.
Yeah.
So the first African male winner in a big city marathon was in the mid-1980s, and the first female winner appeared in the mid-1990s.
So yeah, to answer those questions, you just have to basically wait for more world records. I don't think it affects too much before about 75 or 80. I mean, the real uncertainty here, I think, is my estimates between, let's say, 75 and 95, right? Where you just don't have, as you point out, you don't have the African runners in there. You got fewer women than men, et cetera. And so that will change as we get better data. And I think it will probably unlikely to change the linear estimates or the transition age maybe, but it may change the quadratic estimates and make it so people are, it's encouraged people even then faster, right? I mean, it's even better for humans because I'm going to get less decline between 75 and 95 than I now estimate.
Great, thanks, Bernd. Georgi is next.
Yeah, thank you very much for the presentation. My question would more be perhaps unnecessarily complicating the model, but in real world applications for towards marathon runners, they're all guided by perhaps different motivations. Like to some of them, it is guided by the sort of psychic impact, and some are doing them for different sorts of charities and whatnot. And there's also a monetary limit that's associated with registration fee. It's not, just enough to run the time at times for some popular marathons like Boston Marathon. You also need to collect, some sort of a total amount to donate to the charity. So my question would be, could that affect sort of the sample size that you've collected in terms of the different people are running for? They basically have different motivation to run it and to qualify, like their qualifying times are not homogeneous across the sample.
So you're asking about my proposal for the qualifying times, not the estimates. Is that right?
Yeah, the proposal, yes.
Yeah, I have, when I talk to these people or wrote, it may be that from what you said, you want to do different than in terms of decline rates. So you want to do something other than my decline rates, because maybe the sample that a runner, the race is using, as you point out, is not quite the elite marathon sample that I have, let's say. So that's, I tell you, that's fine. My only complaint really about this is that they don't have the biology right? Whatever you want to do in terms of whatever you think your population is, don't have it be the case that people get better with age, which they now do, right? So you could pick, whatever decline rates you want, and whatever starting points you want for your qualifying times. Just make it so that it's consistent with, you never get better with age. Yeah.
Great.
As I said, that I have just a hard time. They don't get it. As far as I can tell, at least they don't get it or they don't want to, right?
Thanks, Yogi. Next question is from Pete.
I really enjoyed your talk. The thing that kind of intrigued me, well, when I heard Bernd's question, you are comparing people that are 80 years old to people that are, I guess it's current data. In some ways, they're the same population. So an 80-year-old would have been 40 years old 40 years ago. So I was wondering, it might be interesting to compare the 40-year records to the 80-year records so there'd be the same cohort as they moved up. It would require a lot more data. Do you understand what I'm saying?
Yeah, so you want the world record at age 40 years ago, right?
Yeah, so somebody that's 80. So you compare it. Yeah, that's what I know it's a data mess, but that would kind of get away from what Bernd was getting at. Because it's the same cohort.
One possibly could do a little bit of that. The problem, of course, is the soft times issue. 40 years ago, the world record at age 40 years ago is probably pretty soft.
Yeah, and it's true. An 80-year-old now has the same techniques to train. So it's not just the technology.
I can't just follow. Somebody asked, well, can I just follow some elite athlete over 25 years, right? But an elite athlete has good years and bad years. He's injured or she's injured sometimes, etc. So it's and I can't do that either. The one encouraging thing I have is I have a couple. It's on my website if you want to see it. But I've got a couple of people that have stayed more or less on the line that are not elite runners. So so there's some small evidence that at least some may be able to do that. But even if you don't stay quite on your line, as I said, the question, does that have anything to do with economics and stuff? And, basically, I would say the results suggest that decline rates are not as bad as you might think in the 80s and 70s and 80s. So that it might then have something to say about retirement policies and treatment of old people in general, et cetera, that it's assuming people aren't sick and overweight and so on, just assume they're stay in shape, then they're pretty good.
Thanks.
Great, thanks, Pete. And then back to Wayne.
Yes, that does raise the other question I was going to ask, which is, so this is frontier, most elite performance, and we're using that as a measure of, you're using that as a measure of physical decline. And so what data is there about cognitive decline, and how do these two compare? So I think thinking about academia, for example, or in like different kinds of professions, you got a mix of physical, health and fitness, and then cognitive, I don't know, whatever, others as well. But it would be interesting to put those two side by side, whatever the best data is about cognitive decline. And so it'd be really nice to think about, okay, here's a physical and then a cognitive. And to the extent that we're really interested in potentially thinking about how would one decide the length of time in which people can function in jobs, pilots have mandatory retirements and so forth. That would be a nice, whatever other literature is out there that somebody else has done that you could just, put next to yours.
Yeah, there's an early paper by Dan Hammermesh and my late wife Sharon Oster on publications by age. So they're looking at productivity, some estimate of productivity of academics using publications by age. So they're estimating decline rates, and I don't know if it's cognitive, but they're estimating decline rates at least with respect to the number of papers that you're getting published. And there's other literature of that sort where people are looking at, especially Hammermesh has continued doing this. I said I have one thing on chess. I can do this for chess. You can get the best record. I forget the number, but each chess master has some number. So you can get the best number by age for chess. And so I did the same thing for chess. And there is some decline. 80-year-old chess players, their best ever 80-year-old chess player is not as big a number as the best, 40-year-old chess player, 50. So you can get some decline, but as I said, fortunately, the decline's pretty low.
Right.
You decline, but it's not the numbers you're looking at in this paper today.
Right. Well, what's wonderful about your data is it gives the idea of the frontier. And of course, most of us mere mortals aren't on the frontier. And so one would like to have some measure of median or average or some sort of thing. So it's wonderful to have your frontier data, but both, in these various domains.
Well, you could possibly be on the frontier and decline rates, percent decline rates, right? And
Right.
You don't have to be an elite athlete. You just have to decline at the same percent.
Right.
So you could try that. You could try that.
I will.
Thanks, Wayne. I mean, related, I guess, is obviously you're looking at one person in each age group, and you must have a distribution which obviously thins out as the ages go higher. I don't know whether things like qualifying times for races, presumably these races want the top 5% or something of their, of runners at each age or something. I don't know whether there's some insight you can get from the distribution as you go through the ages as well as just the the world record time.
I don't know. What would I do with it? So I have the world record times. What would I do with the distribution? I don't know.
Yeah, I guess I'm just thinking about, I guess, what's the 95th percentile as you go through
Well,
each age?
one possibility, if I could get the data, which is, I'm not sure how easy it would be, is I could look at the second and third best times ever, right? And that's this freak thing that I just mentioned. If the second best time is way worse than the first best, then maybe I ought to think about the first best time, right? And but it's hard to get data on the second best time ever in races by age. Yeah,
it's true. Yeah. Wayne, did you want to chip back in then? You're on mute.
So back to Bernd's comment that he made, that most of the elite runners are from the Rift Valley, and so they both have special lung development and body type, and all of that, and so they're like the optimal human being suited for running, and especially long distance running, and so so those are very particular body types. So of all the human species, those seem to be like the ideal human species, where they were born, raised, and then their particular body types suited for this. So to some extent, that's like, okay, so for that body type, that's the maximum. What's the maximum, functioning for others who don't have those particular body types? So that's probably different than for the other two events that we're discussing. You're analyzing the swimming and rowing, whether or not there's a body type which is ideal, that then people without those ideal body types then have some other frontier maximum.
Yeah, I agree with that. Yeah, I think I would trust the rowing and swimming more than the running for that very reason. If I'm only picking up, if people differ and genetically differ, and I'm only picking up one group of the genetic group, let's say the East Africans or something, then the results are not that comparative, can't be used by the rest of us, right? Yeah, I agree with that. How big a problem that is, it's hard to know, but there is certainly something there. Yeah.
And then, as you say, whether or not the decline rates and the patterns are any different, those are just the maximums, but right. Yeah.
Well, yeah, the question of these, if the genetic elite athletes, do they decline less? That's the question. Do they decline less? They're certainly faster. Do they decline less is a weaker assumption, but it's still an assumption.
So Dennis had to leave early. They dropped me an email to say that he was interested in the transition ages. I guess the point when you go from the linear to the quadratic, and he thought that they seemed really quite high, and was interested in your intuition on why those transition ages seemed quite so high.
Well, that's just the data. I was a little surprised too, but this has been true for 35 years, right? The estimated transition ages are in the 60s or sometimes 70s. And the data just suggests percent linear declines up to that point. And the standard errors are fairly small. So I think it's that's one of the encouraging features for humans, right? The transition age isn't so bad. I mean, the neat thing about it is I can actually estimate it. I don't have to assume it. And so I can just say that's what, and the thing is that age doesn't change a lot across events, within a certain group, swimming, they're all in the kind of the same ballpark. So I think there's some evidence, the data I think are telling us something there.
Mm-hmm. Yeah, definitely encouraging. No doubt about that. Any other questions and comments that folk have? One kind of observation that sprung to mind when you were presenting was it's something I've only read, and I've got no idea about the robustness of the the data, the sample sizes, and so on. Obviously, they're not random, but I've read articles that tell me that women are faster when you get to ultra marathon distances. So, you know, what is it, 50 kilometers and more. I don't know how that fits in with you know, these decline rates and the work that you've done so far.
Well, if I had, yeah, I mean, one thing is about the level, right? How, and then the other is the percent changes. So if I had world records by ultra marathons by age and gender, you know, I could do the same thing as I did in this paper and see. I mean, you can do two things. See, is the difference the intercept smaller? You're arguing really basically the intercept is smaller between men and women for, say, ultra marathons and just for marathons, right?
Yeah,
in percent terms. And you could test that, right? With the intercept and the decline rates, who knows, right? Could be even say women are more or less about the same as men in intercept, then are they roughly the same in decline rates or not? And you could test, I could test that with the data, but don't ask me to get world records by ultra marathons by age, okay? I'm not going to be able to do that.
yeah, absolutely. Okay then. Well,
okay.
I don't see any more hands, so thank you very much, Ray. That was a really,
my
really
pleasure.
interesting talk. And we don't meet next week. We meet the following week when we have Stefan Szymanski from the University of Michigan presenting discrimination and the white captain era of West Indian cricket. So thanks again, Ray. Thanks, everyone. Great to see you, everyone, and look forward to seeing you in 2 weeks' time.
Great. Thanks a lot. My pleasure. Thank you for inviting me.
Cheers, Ray.
Yeah.